Hi everybody, Shai here. And today we're going to be discussing a very important problem I've been working on for the past 3 years. And that would be my work toward producing an equation for the factorial. So the factorial can be expressed as the progressive product of increasing numbers, and that would be written as 1 times 2 times the next number times the next number all the way up to x. And the general solution for solving this factorial is usually expressed as x times x minus 1 factorial. And this is the faster way of solving the expression x factorial. And so this is our mathematical object of interest. And this is of interest to us because there's another object we can consider. And that would be the progressive sum of increasing numbers. And that would be written as 1 plus 2 plus the next number plus the next number all the way up to x. And an equation also exists for this progressive sum. Gauss figured this out in the late 1700s. The equation is x times x plus 1 divided by 2. So we have an equation for the sum, but as I look through whatever available literature there is, I haven't seen any notation for the progressive sum in the same way it exists for the progressive product, otherwise called the factorial. So because this notation doesn't exist for the sum, we have to invent something. So we'll assign the hashtag to x and call this the summandial of x. It will represent the sum of numbers between 1 and x, and it'll serve as an analogy to the factorial, which uses the exclamation point. And the reason why we call this hashtag the summandial is because for the factorial, it refers to factoriand, a number that's multiplied by another number. So for the summandial, we would use the word summand, a number that is added by another number. So when we do this, it becomes easier to see an inconsistency. The inconsistency can be spotted due to the symbology of the factorial. We see that we have an x factorial, so there's a factorial on the left side here. And then on the other side, we have x times x minus 1 factorial over on the right side. So there's a factorial on the right side as well. But then let's look at the sum. There's a summandial or a hashtag on the left side. But then on the right side, we have x times x plus 1 divided by 2, in which there is no summandial on the right side. Now, this is suspicious because in algebra, we're taught to isolate important variables to one side of the equation to solve them. But clearly, we see that for the factorial, it hasn't been fully solved because there's still a factorial present on both sides of the equation. So what this indicates is that the factorial equation is not truly solved, and that there may exist a more general equation that is more similar to behaving like the summandial. So first, I'll show you the way in which the summandial is definitively faster by hand, and then I'll prove it through computation. So let's do it by hand. So we'll choose a big number. We'll go with 10. And we'll take the summandial of it. And we'll even go slowly for the summandial, and you'll see that it's much faster. So let's plug it in. We got x times x plus 1 divided by 2. So that'll be 10 times 10 plus 1 divided by 2. That's step 1. Step 2. We have 10 times 11 divided by 2. That's step 2. Step 3. We have 10 times 11, that's 110 divided by 2. And that's step 3. And then step 4, 110 divided by 2, well, that's 55. Okay. So we got to the answer in 4 steps there. Now let's go ahead and check the factorial. So again, we'll plug it into the equation. So we have x times x minus 1 factorial. So we can just know that x minus 1 in this case would be 10 minus 1, and that would be 9. So we have 10 times 9 factorial. Okay, that's step 1. Step 2, repeat the process. So we'd have 10 times 9, that's 90, times 8 factorial, and that's step 2. Step 3, 90 times 8, 720, multiplied by 7 factorial, and that's step 3. And then step 4, 720 times 7 is 5040, multiplied by 6 factorial. So one thing to notice about all this is that when we plug values into the sum, it doesn't matter how large the number is. It will always only take 4 steps. Whereas for the factorial, it will always take an input number of steps. So just notice here, we still have a 6 factorial. And so what that indicates is that if we were to continue the process, we would still have to take 6 more steps in order for us to get to the solution for the factorial. So if our input is 100, it would take us 100 steps to solve it, as opposed to only 4. And that is just a minimum. Keep in mind, we even sped up our solve of it. So this is all very important, because the factorial is often used for considering combinations of things. And if an equation were to exist that would allow these combinations, even very large combinations, to be near instantly calculated, then it may completely change the way that computers operate. So that's a very important thing to keep in mind. And just how much more fast is the sum and dial compared to the factorial? Well, let's find out. I went ahead and programmed the equation for the sum and dial, and then compared it to the algorithm for the factorial. And here is the result. Now that we have some intuition of how the sum is probably faster, we're going to go ahead and prove it computationally. So I have here the equation for the sum as provided by Gauss, and then the general algorithm for finding the factorial. Let's see how fast each one can be calculated using 10 million as our input. All right, so this first number here is how fast it took to calculate the sum, or the sum and dial, and it took 2,400 nanoseconds. So that's about 2 millionths of a second. And then for the product, or the factorial, it took about 10 million nanoseconds, so 1/100th of a second. Naturally, we can see from a practical perspective, the sum and dial is a much faster process when we use the equation, being that it calculates in about 2 millionths of a second. So what happens when we calculate the sum and dial without the equation, and instead use the algorithm, adding the numbers one at a time? What we find is that it will take the same amount of time as factorial approximately. We can see that the numbers are both quite large. So that provides definitive proof that the sum and dial can always be solved in a fixed number of steps using the equation, and that such a method does not currently exist for the factorial. And this would serve as definitive proof that an equation for the product, as determined through our study of the factorial, does not currently exist. Now the question is, can we find the product equation? The good news is we probably can, but we'll see what I mean by probably in just a second. So we know that calculating the factorial is presently slower than calculating the sum and dial, and this suggests that an equation for the product of numbers does not presently exist, but that an equation for the sum and dial does. So perhaps we can figure out what the true equation for the factorial product is. How do we do that? My first approach was relatively simple. I used the same method that Gauss used to find the sum. Unfortunately, this didn't yield any important results other than various observations that were interesting. But eventually I figured out a way that's very likely going to produce an equation for the product. And by the way, moving forward from here, I'll be using factorial and product interchangeably, since really in this circumstance they mean the same thing. So in order to algorithmically determine the product, there is a specific approach we might take. It involves constructing every possible expression up to a specified length with an upper bound imposed on the terms. So first we have to specify the length and upper bound. So let's say our expression is of length 5 and our upper bound is 7. We would start by writing length 1 for our expression, and then we would check all expressions of length 1 up to the upper bound. So we would have 1, 2, 3, and so on, all the way up to 7. And then once we reach that upper bound, we would loop back around to 1, and then include the first operation. Let's say that's a plus sign. We would then programmatically have to add some number, so we would add a 1, and then we would replace the operation with some other operation like minus, seeing how the results change. Once we do that, we can upgrade our number. We now might have 2 plus 1. We then repeat the process, having 2 minus 1, 2 times 1, and so on. And if we repeat the process, we will inevitably arrive at the following expression: 7 to the power of 7, 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 once we've exhausted all the operations for the full length of the expression up to the upper bound. And this is one way in which to calculate every possible expression in general. And the question is, can we use this method to find general equations? The answer is yes, it can be used to find general equations. And we can definitely use this sort of algorithm to find the equation for the sum and dial, actually. And so that's what we're going to do. And then we'll see if we can do the same thing for the factorial, so that we would have some kind of equation for the product. So let's do that. So as you can see, we're going to run the code, and it generates a whole bunch of expressions. And so what the code does is systematically generate expressions for every number less than or equal to the upper bound for every term, and also the upper bound for the specified expression length, while taking every possible combination of operations. Here we set the length to 4 and the upper bound to 4. After generating every possible expression, we can check to see if a solution might be produced by taking one of our candidate expressions and evolving the equation to find out if incrementing a number in a specified slot will yield a general pattern. So for some of these expressions, we want to see if we satisfy a solution upon incrementing at one or more slots. And so as we can clearly see, we take an expression and we start increasing the values in one or more slots until every possible variation is produced. By doing this, we create a chain of expressions that follow discretely from one to another, and so by pairing each incremented expression with the original, we can see if the pattern of the sum and dial is being replicated. And this is the way in which the equation is found. By incrementing a number by 1 in various slots, we can make a variable substitution and determine if the integrity of the sum and dial pattern holds. After running the list of possible solutions through various incrementations, I found all of the expressions that yield some kind of direction toward a general equation to the sum and dial. But we can refine the search more. We can now substitute a variable wherever a pattern was found, and so we can run our next algorithm, and it yields us a list of possible solutions in which one or more variables were substituted. We then sort these equations by the number of times we made a substitution, so we can see which equations have the most substitutions, knowing that the sum and dial has 2 variable substitutions at minimum, one in the term x and the other in x plus 1. It also has 3 variable substitutions if written as x times x plus x divided by 2. And so that would be useful if the factorial had a similar kind of form, in which the solution contains a substantial number of substitutions. And so that's why we sort the expression by variable count. Lastly, we will filter for whether these generated expressions with the variable substituted satisfy the sum and dial. So after producing a general form for various expressions, we will now match each expression containing the variable substitutions with the sum and dial to see if a general pattern of being equal is produced. And there we go. All that's left is every possible way to write the sum and dial. So we successfully reproduced the Gaussian sum from pure calculation. What's next is to compute the product. We can run the program for expressions of at most length 5 and upper bound 5, and with those parameters an equation was not found. Changing either of these parameters to a higher amount on my computer will cause the program to stop, because the computer I'm using runs out of memory. I also quadrupled the storage, and this didn't improve anything. However, there is another method that we can try. So, we have to use a new method since our old one saves too much information. What if we tried a similar approach that doesn't use storage? Well, the method for saving storage is actually much more simple and easy to use. It consists of generating a number up to a specified size. Let's say we choose 7,717. Now, in order to calculate every possible expression, we would have to count up to that number. But instead of just counting, we would include operations in between the digits. So once we count to 10, we would count 1 plus 0. We would also count 1 minus 0 and 1 times 0, and so on. And we would do the same thing for 11, counting 1 plus 1, 1 minus 1, 1 times 1, and so on. Naturally, we might generate a more arbitrary expression like 3 plus 4 times 2 to the power of 3, in the case of 3,423, counting up to 7,717. All we have to do is generate all possible combinations of operations and put them in between every number we make. So let's do that. All right. So we generate the expressions without storage by adding operations in between the digits, and again we use an incrementation method to generate our potential solutions. Doing so allows us to generate some expressions of length 6, whereas before we could not. Now this may not seem like a big improvement, but whereas before we could generate no potential solutions, here we could. There were also expressions that our previous method missed that could be generated. So we actually see multiple equations of length 5 and 6 that were generated, and these equations produce accurate results for the factorial up to input 3. As for input 4, it produced results yielding equations equal to either 22 or 34. And that's particularly worth noting because 4 factorial, which is equal to 24, is coincidentally located between these two numbers, 22 and 34, although it is closer to 22 and generates 22 more often. The point is, the algorithm appears to be approaching the value 24, which we're looking for in some way. And so this is definitely worth gathering more information for moving forward into the future. So we were able to expand our pool of results. Although we can't find an equation just yet, the program still depends on speed rather than storage space, and so a stronger computer is still needed. Because of this, it's clearly deducible that our methods will necessarily only work with a powerful enough computer, and this is good information to know at the very least. It's also good to know that this algorithm can be used to determine the sum and dial as well, and that our reconstruction of the sum is guiding us toward the right direction. And so that's where we have to stop, because of our computer limitation. Even so, the fact that we could determine the sum is a major indication that this exact algorithm can be used to find the product, if linked with a particularly powerful computer. And so for now, that's all for our computational adventure. All right. So keep in mind the initial code I produced isn't perfect. So if you check it out yourself, you'll probably notice some things like expressions being missing and incrementations being off. But the second method works perfectly, and I would encourage you to run it yourself, as it could be fun to see the numbers become incremented and then substituted with variables. Another thing to note is the real nature of this factorial equation. Specifically, it's important to notice that whatever solution to the factorial equation we're given is actually just a reduction of the original expression by one step. So not entirely the kind of solution we're looking for, because we still have to run calculations. And so yes, we could generate the solution for the sum, but not for the product. We learned that we need a sufficiently powerful computer in order to generate the product beyond possible solutions of length 6. And this is of course incredibly valuable progress because it leaves room for hope that the equation will one day be produced. The solution is really very near to being discovered, and my hypothesis is that the solution is some expression less than 100 terms in length. So I'm excited to see if it exists, and if it does, what the equation looks like. This progress is also deeply important because it points to the fact that a general solution for the quintic might be solvable, whereas before it's been considered not possibly determinable. So my goal is to also use this algorithm to solve the quintic. In particular, my goal is to use more arbitrary operations like distributive addition, which is the additive form of distribution, to see if such functions would produce solutions to the quintic. I think that could be an interesting approach that could produce new forms of algebra. I would love to know about any thoughts on the subject of the factorial and the sum and dial, and even the quintic you might have. So feel free to let me know what you think in any way you can. Otherwise, I hope you enjoyed. Have a good day. And this is Shai, signing off.